I mean, with all these online, one can kind of virtually meet a lot of people, and I see Hemant Bhatte is there, whom I would be seeing after long, long years. Hemant?
Unmute. Yes, Dipendra, I'm here.
Yeah, no. So, I came to Pune many years ago. You may have organized one of those activities.
Yeah.
And I remember coming to your house and all that. And but that's at least 5 years, at least.
Yes, more than that. I've been retired for 4 years. So, anyway.
It is certainly an I'm sure ISER was there very much then. It cannot be much more, maybe 6-7 years.
Yeah. Good to see you.
Good to see you, Hemant. Yeah. So you are settled in Pune.
Yes, very much so.
Yes. Nice. No, I keep getting St. Xavier's College, something or the other. Are you on the mailing list?
Actually, not. I'm not, I think. I haven't got, but
okay. So
anyway.
Recently I got to look at their college magazine from 78, 79, and it had your name.
Oh my God.
Yes. No, it had your name. And, I was just looking at it. They have put up all the old magazines, college magazine.
Sure. Good idea.
Good. All right. So maybe, shall we
start? Yeah, I think we can start now. Yes.
2 minutes past the hour. Okay. So welcome everyone to these series of lectures. I'm very happy to welcome Anwesh Ray from University of British Columbia, who will give an overview of the TaylorWiles method. Thank you, Anwesh, for agreeing to speak in this seminar, and please go ahead and lecture.
Thank you, Dipendra, for this wonderful introduction, and I would like to thank all the organizers for this initiative. So the purpose of my lecture is to give an overview of the TaylorWiles method. So whatever I'll say is probably going to be very well known to the experts. Also because, the construction is very technical, I will also be sort of I will also be sort of not going into a lot of the details, which, a lot of the experts will be aware of, and I'll just try and simplify some of the notation as a result. So let us begin with some generalities, and this is going to be notation throughout this talk. So I'm going to fix an algebraic closure Q bar of Q, and the absolute Galva group is the Galva group of Q bar over Q. And so topologically, we can sort of think of this as follows. So given any number field L, the Galva group of Q bar over L is going to be an open subgroup of this Galva group. And then all of these groups give us a basis of open neighborhoods around the identity. And then given a prime number P, the p-adic integers ZP will be the inverse limit of Z mod P the n, and QP is going to be the fraction field of ZP. So given a finite dimensional QP vector space, V, suppose we have an action of the absolute Galva group on this finite dimensional vector space. So we can sort of think of this as a Galois representation. So what that means is rho V is the associated homomorphism from the absolute Galva group to GLN of QP. So here GLN of QP is just the automorphism group of V, which is isomorphic to QPVM. So such a homomorphism actually gives a representation of the Galva group on this finite dimensional vector space. And we sort of describe that via this homomorphism. So when we have such a homomorphism, if it is continuous, then there always exists a certain ZP linear lattice. So there's a lattice L isomorphic to ZP the n contained in this vector space, which is actually Galva stable. So given such a lattice, we get an integral Galva representation. And now this is going to be a homomorphism from the absolute Galva group to the automorphism group of lattice, GLN of ZP. So notice that now we replace QP with ZP when we choose a Galva stable lattice. So what are some examples of Galva representations? So we've talked about this previously, but I just want to recall some of these notions. So let E be an elliptic curve of Q, P be a prime number, and let's say N is a positive integer. So E sub N is throughout going to be the N torsion subgroup of E sub Q bar. And now the point here is that E is actually a torus. So I can think of E as analytically as a complex manifold, as the complex numbers modulo lattice. So here the lattice is just two copies of Z inside the complex numbers. And so let's just note that by lambda. So then the N torsion subgroup, E sub N, is sort of identified by N with N inverse lambda mod lambda instead of C mod lambda. And one can see that this is just two copies of Z mod NZ. So we get two copies of Z mod NZ from elliptic curve, from the N torsion elliptic curve. But this is what it is abstractly as a group, but it also admits a Galva action. So the absolute Galva group acts on this group, and it gives rise to the sort of non-abelian representation. So a two-dimensional representation. So the point is, like, we want to fix a prime number and get a representation for every single prime number. So let's fix a prime number P. So multiplication by P gives us a map from the P to the N plus first torsion to the P to the N torsion. And as a result of this, we get a system of maps. So for instance, we get a map from EP squared to EP, and then we have a map from EP cubed to EP squared, etc. So we get a system of maps, and the idea is to take the inverse limit of the system. And the inverse limit is what we call the Tate module, the p-adic Tate module, which we denote by TP of E. So this seems very complicated, but this is essentially the object on which the absolute Galva group acts. So it is not hard to show that TP of E is just two copies of ZP, the p-adic integers, but it's also equipped with the Galva action. So this is the lattice associated elliptic curve on which the Galva group acts. So the absolute Galva groups on this acts on this lattice. So it gives rise to this representation rho from the absolute Galva group to the homomorphism from the absolute Galva group to GL2 of ZP, the automorphism group with lattice. So notice that we get one such homomorphism for every elliptic curve of Q and every prime number P. And throughout, we're going to use the following notation. So Rhobar is going to be the mod P reduction of this homomorphism. So we look at this homomorphism, then we go mod P, we get a map to GL2 Z mod PZ. So this is going to be the residual representation. So throughout Rhobar is going to be called the residual representation. So a little bit more, notation and a little bit of Galva theory. So the point here is that we look at these global Galva representations. So Galva representations associated to the absolute Galva group of Q. And once you have a global Galva representation, we can localize it at different primes. So we have a global object and we localize it at different primes, and then we sort of study the local properties of these Galva representations. And these local properties are actually going to be very important in sort of understanding, properties of Galva representations associated with modular forms and elliptic curves. So given a prime number L, let G sub L be the absolute Galva group of QL. So that this is the Galva group of QL bar over QL. And we have, so suppose we take this inclusion of Q bar into QL bar. So one can see that this gives rise to an injective map in the other direction. It's going to give a injective map from G sub L into the absolute Galva group. And G sub L is sort of associated with the decomposition group in L. And now if you have a global Galva representation, so essentially rho is representation for the absolute Galva group, we can restrict it to any of these local Galva groups G sub L. And I'm going to denote that restriction by rho / L. So this is restriction of rho to G sub L. So I want to sort of talk about what it means to be unramified. So let's consider the Galva group of FL bar over FL. So here FL is the finite field with L elements. Now this Galva group is actually isomorphic to Z hat. And it's generated by the Frobenius element, which takes X to X dl. Now, what we can do is we can lift this Frobenius element, sigma L bar, to Frobenius, to an element sigma L inside G sub L. So we can fix such a lift. Sigma L is called the Frobenius. And the kernel of the reduction map from G sub L to the absolute Galva group of F of L is called the inertia group. And the inertia group is going to be denoted by isobel. So now we have this global Galva representation. We say that rho is unramified at L. If when we restrict rho to isobel, we get the trivial representation. And if rho is unramified at L, then rho applied to the Frobenius is independent of the choice of lift. So we can actually get a matrix rho sigma of L, which is independent of the lift because rho is unramified. So I just want to sort of say a few words about how the Galva representation sort of recovers properties of the elliptic curve. So we have an elliptic curve E over Q, so that E of L be L plus 1 minus the number of points of E over FL. And first of all, this Galva representation associated elliptic curve is unramified at all primes, L not dividing N times P, here N is the conductor of the elliptic curve. And for every such prime L at which the elliptic curve, the Galva representation is unramified, we look at the characteristic polynomial of Frobenius, and it's explicitly given as follows: it's x squared minus a sub L plus L. So essentially, a sub L of E, which is kind of like the Fourier coefficient at L, can be recovered by taking the trace of the Frobenius at sigma of L. So in that sense, it's like the Galva representation sort of knows these Fourier coefficients. So it knows a lot about the elliptic curve. So we discussed elliptic curves, which is sort of like the prototypical case of the Galva representation. Now let's just talk about modular forms and how we get Galva representations from modular forms. So first of all, let H be the upper half plane, and SL2Z acts on the upper half plane by fractional linear transformations. And consider the following congruence groups. So gamma naught of N, this consists of all matrices in SL2Z, which reduce to upper triangular matrices modulo N. And gamma 1 N consists of all matrices, which reduce to unipolar matrices modulo N. So gamma 1 of N is a subgroup of gamma naught of N. So given an integer k greater than or equal to 2, let Sk of gamma 1 of N be the space of cusp forms of weight k on gamma 1 of N. Now we associate the space of cusp forms, we have an algebra of Hecke operators. So there are three types of Hecke operators. So for every prime not dividing N, we have a Hecke operator called TL. For every prime dividing N, we have an Atkin-Lehner operator, U sub L. And then we also have the diamond operators because the group is gamma 1 of N. So I'm not going to specify exactly what the definition of these operators are. They can be defined in terms of the Fourier expansions. But the point is that these operators are the operators that generate the Heike algebra, and they tell us a lot about what the Galva representation does. I hope that in the later lectures, these operators will be explained in a little bit more detail. But for now, I'm just going to sort of assume that we have some familiarity with these operators. Now, suppose f of z is a normalized Hecke eigencusp form. So essentially what that means is we have this modular form on gamma 1 of N, and it's normalized in the sense that it's the a sub 1 is actually set to be equal to 1 after multiplying it by a constant. And it's a Hecke eigenform in the sense that all the Hecke operators act on it by a scalar. So suppose we have such a Hecke eigencusp form, then it's known that all the algebraic, so all the Fourier coefficients are actually algebraic numbers. And not only are they algebraic numbers, but they generate a number field extension of Q. So they generate a field extension of Q, which has finite degree of Q. So we get a finite extension of Q, which contains all these Fourier coefficients. Let's call it F. So let's take this number field F. Let's choose a prime P, and let's also fix a prime frac P above P inside the ring of integers. Then what we do is we take the completion of O sub F at frac P, and let's call that O. Now, Deline's construction, which involves some knowledge of italic homology, gives us a two-dimensional representation associated to F and the choice frac P. It gives us a representation from the absolute Galva group to GL2 of P, associated to F and frac P. So later I'll sort of explain how this sort of works out in the case when the weight is equal to 2. And the other thing about this Galva representation is that it recovers properties of the modular form. So for instance, once again, we take the characteristic polynomial at the Frobenius at a prime naught dividing n times p, and then we recover the Fourier coefficient, E sub L, and then we also recover the Levin type and the weight. So the point is that it sort of tells us a lot about this modular form. Okay.
Can you repeat
So
that?
sorry. So what I was saying here is that so this representation rho sub f of p, this representation is unramified at all primes not dividing n times p. So here n is the level. And for every such prime, every prime L not dividing n times p, you take rho applied to the Frobenius. So that's a matrix. That's a 2 cross 2 matrix. You take the characteristic polynomial that 2 cross 2 matrix, and then the characteristic polynomial is given by this equation. So E sub L is the Lth Fourier coefficient of the modular form. And here psi is the Levin type character. So the point here is that the modular form is sort of determined by its Fourier coefficients, and you can sort of recover all these Fourier coefficients from the Galva representation itself. So you take the traces of the Frobeni and you sort of recover all the Fourier coefficients. So in that sense, it sort of like completely knows the modular form. So it sort of contains a blueprint of the modular form in that sense. Okay, so now what does it mean for the elliptic curve to be modular? So we say the elliptic curve E over Q is modular if there's a Hecke eigenclust form or weight 2 on gamma naught of n, such that the associated representation rho fp is isomorphic to the representation rho e. So if the Galva representations match up at a given prime p, then we say that E is modular. And it is a fact that if this isomorphism holds for any one prime p, then it has to hold for all primes p. And that is because the set of, these representations rho fp form a compatible system of Galva representations. So here are the main theorems. So first, Wiles and Taylor-Wiles showed that every semi-stable elliptic curve E over Q is modular. And then later, Broy, Conrad, Diamond, and Taylor sort of improved the method, Wiles and Taylor-Wiles, to show that every single elliptic curve E over Q is modular. So the purpose of today's lecture is to sort of explain, how the first theorem, for instance, is proved. So like essentially give a like very brief sketch of the different moving components behind the method of Taylor-Wiles, the initial conception of Taylor-Wiles. Okay, so first what I want to say at this point is that so far I haven't said anything very concrete about the Galva representations associated with modular forms. Since we are interested in the case when the modular forms are weight 2, we can actually say a little bit more about the Galva representations. The point is that they actually arise from a billion varieties. So that x1 of n be the modular curve associated to gamma 1 of n. So you have the upper half plane, you go modulo gamma 1 of n, you get a quasi-projective curve. So in other words, a Riemann surface with some points sort of not some whole punctures in it. Then we take the projective closure, we get an algebraic curve. You have something which is the structure of an algebraic curve. And then the point is that we can take this algebraic curve and take the Jacobian of this algebraic curve. So the Jacobian is like a large torus. So just like an elliptic curve is a torus, the Jacobian is a higher dimensional version of the torus. So it's like it's what's called an abelian variety. The point is that from an abelian variety, one can get a Galva representation as follows. So we fix a prime number p, and just like what we did with elliptic curves, we just construct the Tate module in the same way. So we take the inverse limit with the PDN torsion of the Jacobian, and this is called the Tate module. And now the Tate module is some 2n dimensional. So this is a free ZP module of dimension 2n, where n is the dimension of this Jacobian. Sorry. And then once again, the absolute Galva group acts on this lattice, this 2n dimensional lattice, and gives rise to an integral representation from the absolute homomorphism of the absolute Galva group to GLN of ZP. So, okay, so we have this large representation, but the point here is that this representation sort of, decomposes into like smaller representations. And those are the representations that arise from modular forms of weight 2. So what we do here is, So we fix an isomorphism between the complex numbers in QP bar. And so such an isomorphism is extremely discontinuous, but we fix one such isomorphism. And when we fix an isomorphism, we can actually view QP as a subalgebra of C. And the reason for doing this is now we can define a Hecke algebra. So T sub n is the ZP algebra generated by the endomorphisms of S2 gamma 1 events, so the endomorphisms of the weight 2 cusp forms on gamma 1 event, which is generated by the Hecke operators. So it's the same Hecke operators as before. So T sub L, U sub L, and the diamond operators. So these Hecke operators, I mean, so they generate the Z algebra, but we can sort of extend that to a ZP algebra. Now the point is that the T modulo Jacobian is the module over this Hecke algebra. The point is that every Hecke operator T gives rise to an endomorphism of the Jacobian. And as a result, it gives rise to an endomorphism of the Hecke module, to the T module. So the T module can be viewed as a module over this Hecke algebra. So now suppose we have our Hecke eigenform F. So the Hecke eigenform gives us a map from T sub n to O. And what this map does is it just takes our Hecke operator and sends it to the scalar associated to the Hecke operator. So phi of f of t is the scalar such that t acts on f by the scalar phi of f. So this is just like, this is the map associated to the modular form phi of f. And then we take the maximum ideal generated by the kernel of phi of f and the uniformizer of O. It's called that frac of m. And then what we need to do is we need to basically we need to localize the Hecke algebra at m. And when we do that, we tensor the Tate module, localize it m with O, and we get our O lattice. So we get 2 copies of O when we take this tensor product. The point is that the absolute Galva group acts on TP. And as a result, that Galva action sort of gives us a Galva action on this lattice. And that is the Galva representation associated to the modular form in the weight case. Now, in the higher weight case, the point is that the idea is sort of like generalization of it's sort of related to this sort of idea. And instead of using the Jacobian, one uses a Tal cohomology instead. But that is a subject of another talk. Right now, we just care about the weight 2 molar forms. Okay. Now, one of the main ingredients in the TaylorWiles method is definition of Galva representations. And so this is a theory which was invented by Miser, and it sort of was invented in a slightly different context. But the idea here is that by considering deformations of Galva representations, one can sort of, very formally recover the Hecke algebra as kind of a deformation. Okay, so I just want to start with some very basic definitions. So K is defined extension of QP, and O is going to be the valuation ring. It's always a ZP algebra, it's a valuation ring. And so I see a comment in the chat.
Welcome to the postgraduate program in artificial intelligence and machine learning.
Okay, so O is not local. I thought it was a number ring of KF. Okay, so yeah, so previously O was, so we had O sub F, which is the number ring of the field of Fourier coefficients. And then we actually localized that, we completed that, sorry, at a prime ideal frac P. And that was O. In this setting, we're just taking some valuation ring. But in our applications, it's going to be the completion of the number ring at a prime ideal frac. Okay, so I hope that was the only question. Okay, so suppose we have a Galva representation from the absolute Galva group to GL2 of O, and then we have the residual representation Rhobar. And the point is that now this Galva representation rho, and you might think of something coming from modular form or maybe something coming from elliptic curve. This lies in a family of Galva representations, which are deformations of Rhobar. So I'm going to come to the notion of deformation of Rhobar in a second. The point is that deformation takes values in a certain very large ring. So it's not necessarily a ring as small as ZP or O or something. It's something a lot bigger in general. So the type of rings we're looking at are rings which have a presentation of the following form. So a coefficient ring is a ring which is a complete local Noetherian O algebra, such that when we look at the residue field is isomorphic to F, where F is just the residue field of O. So, okay, that's a lot of adjectives, but what we want to keep in mind is a ring which is the following form. It has a presentation of the following type. So we have a formal power series ring in O in M variables, and we're going modulo a number of relations. So this is basically the type of ring that we care about here. So what's an R lift of Rhobar? An R lift is just a representation from the absolute Galva group of GL2. Such that when we compose this representation with the after going modulo the maximum ideal, we recover Rhobar. So we have this representation of GL2 of R, and then we sort of go down to, we go modulo maximum ideal, we sort of recover Rhobar. That's what an R lift is. And suppose we take two R lifts, row 1 and row 2. Then, I'm sorry, this is a typo, this should be GL2 of R. So two R lifts are strictly equivalent if they are conjugate by a matrix in GL2 of R, which sort of reduces to the identity modulo maximum ideal. So this is a typo, that this spot there should be an R. Yes, but this is just a notion of equivalence between two R lifts. Okay, so a deformation is just an equivalence class of such lifts. It's kind of like a fancy word, but that's all it is. Just an equivalence class under this conjugation equivalence. Okay, so we have our Rhobar, and now we want to define some, we want to look at some, we want to talk about the notion of a universal deformation. So in order to do that, we need to fix a finite set of primes S, which contains all the primes at which Rhobar is ramified. So S is the finite set of primes containing the primes at which Rhobar is ramified. In other words, Rhobar is unramified away from S. Okay, so we fix such a set of primes, and GS is going to be the maximum quotient of the absolute Galva group, which is unramified away from S. So this is just, so a homomorphism out of G, taking values, a homomorphism, so if the representation is going from GS to GLN, then that means that it's actually unramified away from S. So this is a little bit of notation that actually helps us. Okay, so we fixed S, which is the set of primes where the representation is not ramified. And so once we fix S, we get a universal deformation. So what this means is that we have a homomorphism from GS to GL2 of R Rhobar. So R Rhobar is a coefficient ring, such that if I take any other deformation, then it actually,
I just came to say hello.
Then it actually arises from specialization. So any other deformation rows of R actually arises from this universal deformation. So if I take any other deformation rows of R, I can take the universal deformation here and then compose it with another map to basically obtain rows of R. So in other words, basically here rows of R is basically for every rows of R, there exists a unique map from R sub Rhobar to R, such that the composite is actually rows of R. So in other words, so if I think of R sub Rhobar, so if I look at spec of R sub Rhobar, then all the R valued points on spec of R sub Rhobar will correspond to the R valued deformations, rows of R. So it's like spec of R sub Rhobar is sort of like a scheme that parameterizes all of the deformations of Rhobar. So it's kind of like representing some moduli problem. Yeah, so here R sub Rhobar is called the universal definition. So this is a really important point. I just want to check with the audience if this point is clear. Any questions about what I've said so far? So I'm just going to pause for a few minutes if there are any questions. Okay, so if there are no questions, let's continue. So the point is that we're trying to like abstractly recover the Hecke algebra by sort of by using these deformation rings. And the point is that any deformation is not necessarily going to come from modular form, because the Galva conditions associated with modular forms have to have some additional properties. So they have to have some, they have to satisfy some local p-adic Hodge theoretic conditions at P, for instance. They have to be finitely ramified, etc. So we have to additionally impose some more conditions at every single prime. So this is where we bring in local deformation conditions. So Rhobar sub L, remember, is the restriction of Rhobar to the local decomposition group G sub L. And when we look at Rhobar sub L, so this is a local Galva representation, we can consider all the deformations of Rhobar sub L. So CLN of O is the category of coefficient rings. And we get a functor from CLN of O to sets. And this functor basically takes a coefficient ring R to the set of deformations of the local representation to R. So it's kind of functorial. So it takes R to the set. And a deformation condition, C sub L, is just a sub-functor of this functor of deformation. So the full functor of deformations is def of L, and C sub L is just a sub-functor. So C sub L has to satisfy some extra conditions in order for it to be sort of representable and relatively representable. But I'm not going to get into those details at this point. What I want to say is that what this means is that for every R, we have a subset of def L of R, called CL of R. And therefore, like a local representation either lies in this set or not. So if it lies in this set, we see that it satisfies this local deformation condition. So in this sense, it's kind of like imposing a condition for every prime L. So if it lies in the set C sub L of R, then we say it satisfies a local deformation condition in L. Okay, so what is a deformation type? So this is what we want to impose on our global deformations. So we fix a set of primes sigma. So sigma is a set of primes outside of which Rhobar is unramified. So in other words, the deformations are allowed to ramify only in the set of prime sigma, which is finite. Furthermore, at every prime L in sigma, we sort of impose a local deformation condition. So what that means is we only sort of specify certain deformations at L to be admissible. So for example, if the representations we care about are ordinary at P, then we can sort of impose an ordinary deformation condition. If they are flat at P, we can impose a flat deformation condition. And then there are other types of deformation conditions. These are all sort of sub-functors of def. So I'm not going to specify exactly what the conditions are, but there are some conditions that should correspond to the Hecke algebras. Okay, so what does the TaylorWiles method do here? So first up, we have an elliptic curve over Q, and then we want to pick a prime number P. So of course, we don't want to pick P equals 2. So let's pick P equals 3. So now there are two cases to consider. The residual representation at 3 is absolutely reducible. So in other words, it's irreducible after passing to the algebraic closure of FP, algebraic closure FP bar. So in this case, it is known that Rhobar actually arises from modular form. So it lifts to something coming from modular form. And this is a result of Langlands and tunnel. Now, in the other case, when Rhobar is not absolutely reducible, then it's due Wiles that you can actually sort of replace the prime 3 with the prime 5. Now, when you look at the residual representation of the prime 5, you are actually okay. So this representation, this residual representation of 5 is actually modular. So this step is called the 3-5 switch. So it sort of reduces us to the case when we can assume that Rhobar is modular at the prime P.
So being absolutely irreducible or not depends upon the elliptic curve, particular elliptic curve.
Yeah, so it depends on the elliptic curve and the prime P. So this Rhobar is the Galva representation on EP, the P torsional elliptic curve. So when the prime P is equal to 3, we look at the 3 torsion, which is just a 2-dimensional vector space over Z mod 3Z. And we have the Galva action on that. So it not only depends on the elliptic curve, but also on the prime. So at 3, it could be, so at 3, for instance, it could be reducible, but at 5, it could be irreducible, for instance. Which is what happens.
Ln it's for the prime 3, right?
Yes, yes.
Not for general prime.
No, no. So like later on, this, so later on, like, so I mean, there has been a conjecture of Serre, which states that if you have an absolutely reducible Galva representation, Rhobar, which is odd, then it, it lifts to something coming from modular form. And so this conjecture of Serre was conjectured for every prime P, and it was settled by Carr and Montenegro. But it was settled in 2009 or 2010. So much after these results were proved. So at the time of Wiles, the result of Langlands and Tunnel was known for the prime 3 when Rhobar is absolutely reducible. And therefore Wiles had to make this 3-5 switch. So if Rhobar at 3 is reducible, then you can actually sort of, then if you look at switch 3 with 5, it actually becomes absolutely reducible and also modular. So there's actually a lot of content.
Switching to 5 guarantees the absolute reducibility.
Yeah, so this is where the semi-stable stability hypothesis is used. So after doing this 3-5 switch, it actually, so if it's reducible at 3, it becomes irreducible at 5. If it's semi-stable, if the elliptic curve is semi-stable.
Okay, thanks.
Yeah, so let me talk about how this R equals T type of result is proved in the minimal case, and then the non-minimal case is a little bit more complicated. So I'll explain what I mean at this point. So N naught is going to be the prime to P part of the Artin conductor of Rhobar. So this is kind of like the minimal level you can get for any modular form lifting Rhobar. So it's kind of like called the minimal level for this reason. And associated to this minimal level N naught, we have the associated Heike algebra. So we take this Heike algebra generated by Heike operators, and we specify the level to be N naught. And then once again, we localize it as a suitable maximum ideal. Just like we did before, we pick the suitable maximum ideal associated to Rhobar, and we localize it at this maximum ideal. So we get something that could potentially look like a deformation ring. For instance, it's local, it's complete, it's not, it has all those nice properties. On the other hand, what we can do is we can sort of specify a deformation type, which is the minimal deformation type. So here, S is the set of primes dividing N naught times P. So at every prime in S, we specify a local deformation condition. So of course, I'm not going to define what these conditions are exactly, but the point is that the residual representation has some representation theoretic properties at the primes away from P. And so the primes away from P use a deformation condition called the Steinberg deformation condition. And at the primes at P, it can, because of semi-stability, it's either flat, or use what's called the flat deformation condition, or it's Selmer, in which case you can sort of, there's a very nice representation theoretic choice of deformation condition. So, one can actually specify these deformation conditions very precisely, but I'm not going to do that in this lecture. I'm just going to try and move on to the global argument here. The point here is that this R naught is sort of the universal deformation ring associated to this deformation type. So what that means is that any other deformation satisfying all these conditions on ramified away from S comes from a specialization of R naught. So for example, we get one such representation coming from T naught. So T naught, like going back to the construction of the Jacobian, T naught has its own Galva representation. Let's call that rho prime. This Galva representation is shown to satisfy all of these local conditions. And as a result, it follows that basically as a result of universality, T naught also rises from a specialization of R naught. Let's call this map phi naught. So we get a map from R naught to T naught, which basically recovers this representation rho prime after specialization. So this is the map phi naught at the minimal level. And now the objective is to show that this map is an isomorphism. So once you show that this map is an isomorphism, then one can actually establish modularity. Of course, one has to show this as isomorphism and also like an isomorphism for all other levels as well. But right now, let's talk about the minimal level. Okay. So so the first step is to prove the isomorphism at the minimal level and then also to prove it at non-minimal levels as well. But the non-minimal level case requires a slightly more involved argument. So showing such an isomorphism between a definition ring and Heike algebra is called R equals T term. So the definition ring is sort of like R and the Heike algebra is T, and then an isomorphism between them is called R equals T result. And this sort of nomenclature is sort of used in more general situations. So like one does prove modularity statements for more general sort of Galva, higher dimensional Galva representations and so on. So this type of a statement is very ubiquitous in the literature since these results were first proved. Okay, so coming back to the what the whole purpose is here. So suppose we have an elliptic curve and we have a definition ring R, not necessarily at minimal level. So the elliptic curve, the Galva representation associated elliptic curve, is the same as the map from R to Z because it arises from the specialization of the definition ring by the universal property. But since R is isomorphic to T, which is the Hekke algebra, this is the same as a map from T to Z. But a map from T to ZP is the same as a Hekke eigenform. So a Hekke eigenform basically will take a Hekke operator to the scalar eigenvalue, so upon specialization. And it's not hard to show that any such algebra homomorphism actually arises from Hekke. So showing such an isomorphism will show that the initial Galva representation rising from a map from R to ZP actually arises from a modular form, which is the same as the map from T to ZP. And this is why we want to show that R is isomorphic to T. Okay, so now the question is, how do we show that R is isomorphic to T? And this is where the TaylorWiles argument comes in. So the idea here is that studying things at minimal level is very difficult. However, what one can do is one can allow for extra ramification at some auxiliary primes. So when one allows for definitions to be to have more ramification at more auxiliary primes called TaylorWiles primes, one can sort of, the structure of these rings actually becomes a lot simpler to understand. And the idea eventually is to pass to some kind of an inverse limit, after which these rings are fully understood. Okay, so this idea is a little bit complicated, but let me just try and go through that for the last 15 minutes of this lecture. So a prime Q is called a TaylorWiles prime if it satisfies the following conditions. Q is not in the set S, so remember that S is a set of primes dividing the ardent conductor times P. Q is also 1 mod P. And the last condition is that Rhobar at sigma of Q, Rhobar at the Frobenius, is semi-simple with distinct eigenvalues. So these conditions are sort of important for the representation theoretic aspect of this. So now suppose Q is a set, capital Q is a set of finitely many TaylorWiles primes. And so associated such a set, capital Q, we can define a new definition condition. So remember that the initial minimal definition condition involved local conditions at the set of primes S, which were the set of primes dividing the ardent conductor. And now what we do is we add more definition conditions at Q. And what that means is we allow for more ramification at Q. So initially, at the minimal definition condition, there was no ramification at the primes in Q. Now we're just allowing, in fact, we're actually allowing any type of ramification at Q. So by allowing more ramification at Q, we actually get a larger definition ring. So R sub Q is going to be the associated definition ring for this new definition type. where we have more ramification Q. And how is it related to the minimal definition ring? There's actually a very nice relationship here. So what we do here is that we let delta of Q be the P primary part of Z mod Q Z cross for Taylor-Wiles prime Q. And then let delta of capital Q be the product of all these groups delta of little q. And now there's the map from R sub Q to R naught, which comes from the universal property. And so what exactly is this map? So first of all, it can be shown that R sub Q is an O delta Q algebra. So not only is an O algebra, but also admits an action of delta Q. And we let A sub Q be the augmentation ideal in this group algebra. So in other words, it's the ideal generated by all elements of the form G minus 1, where G actually is in the group. So it's the augmentation ideal. And then when we take R sub Q and go modulo this augmentation ideal, we actually recover the definition ring at minimum. So there's a very nice relationship between these two definition rings. Okay. So we can do this for definition rings. We can also do it for the Hecke algebra. So once again, we can sort of, there's a very special congruence group we can, over which we can look at Hecke operators, and we can define Hecke algebra associated to this definition type DQ. And we call this T sub Q. We have to localize it as usual at some maximum ideal, which is associated to Rhobar. So this is the Hecke algebra analog. And then again, what we can do is we can see that this Hecke algebra is an O delta Q algebra. And then when we go modulo the augmentation ideal, A sub Q, it satisfies the same property that we get T naught. And finally, by the universal property, there's a map relating R sub Q and T sub Q. It's called this map phi of Q. And so in that, this diagram actually commutes. Okay, so the point is that we get all these. We not only get this map down here, but we get another map up here for every choice of Q. And the idea is to try and show that these maps phi sub Q are isomorphisms as after we pass through some kind of inverse limit. So this is where passion comes in. So here's the first statement, which is actually a very, very, this is a statement which has a lot of content to it. So this can be proved using some Galva cohomological arguments. So the statement is that given there exists a number R such that for every n greater than or equal to 1, there's a set Qn of TaylorWiles primes such that they are all of the form 1 mod PDN. So there is a number R such that for every n, there's a set Qn of R TaylorWiles primes, which are all the form 1 mod PDN. So we can construct this special set of TaylorWiles primes, which are all of the form 1 mod PDN, all of which contain R elements for this fixed R. And we let Rn be the associate definition ring associated to Qn, and let Tn be the associate definition ring associated to, Tn be the Hecke algebra associated to Qn by the recipe specified before. Now, given Qn, we can construct Qn plus 1 in such a way that there are some maps from Rn plus 1 to Rn and Tn plus 1 to Tn. And yeah, so this is again a typo, sorry. So these are not natural maps. I was going to say not natural, but this is a typo again. They are not natural maps. The point is we can get these maps in them. Such that the following diagram can. So once again, the horizontal maps are obtained by the universal property. So the idea is we can sort of like go up a tower. So Rn and Tn are both algebras over this group algebra, which we can represent as follows: O of S1 to Sr, modulo these relations. So here, as n varies, we can see that the power at which you're raising 1 plus S1 all the way to 1 plus SR actually becomes larger. So here the PDN becomes larger as n becomes larger. So if we take the inverse limit of all of these rings, we actually get a formal power series ring in our variables overall. The point is that all of these relations are going to 0 periodically as n goes to infinity. So when we take the inverse limit, we get a formal power series ring in our variables. And the point is that this formal power series ring has a very simple structure compared to a ring like O delta n. So what we do is we take the inverse limit of these deformation rings. We take the inverse limit of these Hecke algebras. So R infinity is the inverse limit of these deformation rings under these maps, and T infinity is the inverse limit of these Hecke algebras. So I can see some questions. What is the relationship between Qn and Qm if n is less than m? Is there any relation? Yeah, so that's a very good question. So Qn and Qm are completely disjoint. The deformation rings and the Hecke algebras are not related to each other by any kind of functorial properties whatsoever. But the idea here is that once you have Qn, then you can construct Qn plus 1 such that there is a map relating, Rn plus 1 with Rn. And so this map is highly non-canonical. It sort of arises from the fact that given n, there are basically there are going to be only finitely many isomorphism classes of Rn for a given n. And it involves the fact that we have infinitely many choices with Qn plus 1. So therefore, you'll be able to sort of recover your choice. It's some kind of pigeonhole principle argument that you're using at this point, but it's not an actual construction at all. There's no functorial relationship between Rn plus 1 Rn. Okay, I'm not sure if that answered your question, but that was a really good question. Okay, right. So, okay, so we pass through these inverse limits, and now things actually become simpler because now there are actually algebras over O infinity, which is a formal power series ring. Okay, and once we pass the inverse limit, we get a map relating them. So this is the inverse limit of all the maps phi n, and this is the map of O infinity algebras. So now the point is, if we show that phi infinity is an isomorphism, then it follows that the map that we started off with is also an isomorphism. So notice that R naught is R infinity modulo S1 to SR. So here S1 to SR generates this augmentation ideal, and T naught is T infinity modulo S1 to SR. So if R infinity is isomorphic to T infinity, then it follows that when you go modulo S1 to SR, you still get an isomorphism. So the initial map that you wanted to show was the isomorphism. You actually have shown that it's an isomorphism after you go up, after you pass this inverse limit. Okay, so now why is this map phi infinity an isomorphism? So the point is that the Hecke algebras act on spaces of modular forms. So Tn acts on a space of modular forms, which is finally generated and free as an O delta n modular. And so let Mn be the space of modular forms on which Tn acts. So that M infinity be the inverse limit of these Mn's. Now M infinity is also going to be finally generated and free as an O infinity modular. So T infinity acts on M infinity in a faithful way. So T infinity also has to be finitely generated and faithful as an O infinity module. So T infinity is just going to be an integral extension of O infinity. On the other hand, it follows from some arguments in deformation theory, some Galva theoretic arguments, that R infinity is generated by R elements. So it's the quotient of O of x1 to xr modulo some ideal. Okay, so as a result of this, what we see is that T infinity has dimension R plus 1, right? And this map is surjective. That is not difficult to show that this map is surjective. T infinity has dimension R plus 1, and R infinity has dimension less than equal to R plus 1 because it's a quotient of this ring. And so therefore, by dimension considerations, the only possibility is that both R infinity and T infinity are basically isomorphic to O of x1 to xr. Because if R infinity is not isomorphic to O of x1 to xr, the dimension will be less than T infinity, right? But this map is surjective, so that is not possible. So the only possibility is that R infinity is actually just isomorphic to O of x1 to xr, right? But then because this map is surjective, that also means that T infinity has to be isomorphic to R infinity. So it comes down to a commutative algebra argument, which is not difficult at all. But the main ingredient here was the fact that T infinity acts faithfully on this space of modular forms when we go to the inverse limit. So phi infinity is an isomorphism from which we actually recover. We actually are able to show that phi naught is an isomorphism at the minimal level. Okay, so I guess the last thing that I should see at this point is that, you know, I just have a few minutes, but what I should say here is that when we are sort of trying to prove an isomorphism at non-minimal levels as well, I mean, it involves like a more technical argument, but it's like the definition ring at the non-minimal level is sort of related to the definition ring at the minimal level. So you try and understand sort of like the difference between these definition rings in a certain sense. And you sort of try and understand the difference between the Hecke algebras in a certain sense. And so you have an isomorphism between the minimal definition ring and the minimal Hecke algebra, and you try and propagate that to the non-minimal case as well. And then when you have this isomorphism for between R and T, that's where the modularity actually comes up. Okay, yeah, so that's all I had prepared today. So thank you so much. And I hope this was actually useful for this lecture series.
Thank you, Anwesh. Beautiful talk. If people have questions, please do ask.
Hello.
Hi.
Hello. I want to ask about the lifting conditions. Means
Okay.
about the lifts. Rhobar means you are saying Rhobar is unramified outside S. Means in general,
Yes.
in deformation, can we have some deformation condition on the lift actually? Means because lift has some more ramifications. Can we fix that? Means some S prime.
Yes. So
And then
I think what you're asking is, right. So definition datum. Let's go back to definition datum.
Yeah.
I'm sorry. There's actually like a lot of slightly technical talk which I haven't like precisely defined everything. But
Yeah.
okay. So what is definition datum here? So this datum. So this calligraphic D is going to sort of give us conditions on our global definition. So here sigma is a set of primes outside which Rhobar is unramified. So for instance, so sigma, so for instance, let's say Rhobar is ramified at 2 and 3, right? Now sigma can contain many more primes other than 2 and 3, but it has to contain 2 and 3. So that is the first thing. But the point is that the larger sigma is, the more ramification you're allowing. So for instance, if sigma is like 2, 3, 5, 7, that means you're allowing ramification at 5 and 7 as well as 2 and 3. You have to have 2 and 3 in there because Rhobar itself is ramified at 2 and 3. Now, the point is that once you have this set of prime sigma, then basically at every prime in sigma, we have a local definition condition on top of that.
Okay.
So for instance, like suppose your primes are 2, 3, 5, 7, and so your Rhobar is ramified at 2 and 3. It doesn't mean that you have to look at all definitions of 2 and 3. You can actually still specify certain like certain local conditions at 2 and 3 at which Rhobar is ramified. So for instance, you can prescribe what's called the minimal definition condition, or you can prescribe some other definition condition. You can prescribe you can sort of allow for all definitions, you know.
Okay.
So CL, for instance, could be all of def L, or it could be something smaller. So like there is one way to think about this is that the set of all definition conditions, you can think of it as some kind of a scheme, and your CL is some kind of closed subscheme inside that scheme. So for instance, if the prime is P, for instance, then let's say your ambient scheme has a certain dimension, and let's say your ordinary, your definition condition could be all ordinary lifts. So that would be a subscheme. But there could be a totally different definition condition like crystalline lifts or something, right? So there's a different subscheme. So like the CL is like, like it's like a subscheme. It's like you're choosing certain types of lifts as like admissible. So it doesn't, it could be something in between, all definitions and just the unramified ones, for instance.
Yeah, but I asked this
I don't know if that's,
yeah, means I asked this question from a different perspective actually. Means in the kind of Faulting's finiteness theorems,
right.
means finitely many representations, if representations are unverified outside some S, if we fix S, means in that sense I just asked, means if we have some more, if we fix some S prime also, means Rhobar ramification is S, some bigger S prime contains S, means can we fix that, and can we ask such type of questions? Means, yeah, it's okay.
Yeah. That's an interesting question. The point here is that like when you're fixing Rhobar and you're fixing S, you're sort of, you have a lot of, so I guess you're talking about the number of Rhobars that can exist unramified outside of fixing.
Yeah,
so here what we're doing is you're fixing Rhobar and then we're looking at all the lifts of Rhobar.
Yeah, how many lifts can be possible?
Yeah. So that's slightly different.
Yeah,
it's a slightly different type of a question.
Okay.
All the lifts are actually like lifting our fixed Rhobar, for instance.
Okay, thank you.
Yeah, but I think like this question about how many Rhobars are there unramified outside of 7 prime S.
Yeah, if we have the Rhobars, then how many rows are there up to isomorphism? If we fix the some S prime.
Yeah. So this sort of thing, it comes up in the theory of like eigenvarieties quite a lot. Like for instance, like eigenvarieties. Eigenvarieties.
Okay.
Yeah. So like when you in definition theory, you're fixing a Rhobar and then looking at all the definitions of a fixed Rhobar. But now when you're constructing, so if you want to look at all the Rhobars which are sort of unramified, outside S, then you have a number of different sort of, you have a number of finitely many choices, and then basically all of their definitions together form, all the definition spaces together form a variety called the eigenvariety. So it has some more structure.
You mentioned is that Q also means Q also you're adding some extra primes Q, Taylor-Wiles prime you mentioned means.
Yes.
So is there something minimal thing or it's
so the point is that you're trying to prove R equals T at the minimal level, and you cannot prove that. You're not able to prove that directly. So the way to do this is to sort of keep adding more, like adding some extra primes Q to the level. So Q is some set of extra primes that you add to the level. Now so for instance, Q1 basically consists of all primes, a set of primes which are all 1 mod P. Q2 consists of a set of primes which are all 1 mod P square. Q3 is a set of primes all 1 mod P cube. So, but they all have the same size and they all sort of mutually disjoint from each other.
Okay.
So like, it's like you're sort of doing this in such a way that you're sort of like, everything is like sort of periodically going to 0. And so your R infinity and T infinity are sort of algebras over this power series ring. And over these power series rings, it's actually easier to sort of prove results using Homology algebra. That's kind of like the idea behind the TaylorWiles method. Yeah, but it is mysterious how exactly they're related to each other. It is a very sort of, these maps relating, let's say Rn plus 1 to Rn, for instance, are very non-canonical.
Okay.
So, but those were really awesome questions. So thank you.
The Taylor-Wiles original method had some more subtle commutative algebra, Cohen-Macaulay rings and so on.
So a large part of this
been simplified over the years.
So after doing all of this, we are not only able to show that the definition ring and the Heike algebra are isomorphic, but we also know something about their presentations. So we know, for instance, your R infinity is O of x1 to xr, and so is T infinity, they're isomorphic. But now you sort of go back to R naught, and so it's O of x1 to xr modulo s1 to sr. So, you know, you have the same number of generators and relations. So this is called the complete intersection problem. So that is a result of this method. But I mean, again, there are a lot of technical points in this whole proof, which I've sort of put under the carpet, for instance, like the semi-stability is used throughout, and then proving these results at the non-minimal level is also something that I've not talked about much. So I mean, all of these, there's a lot of technical, there's a lot more to be sort of unraveled.
For application to elliptic curves, semi-stable elliptic curves, you need minimal or not necessarily minimal level?
No. So, right. So the semi-stability is used in various places. For instance, in like the 3-5 switch step, and also in prescribing the definition conditions at P. There are many other steps in which it is required. But the thing here is that you first prove the isomorphism between R and T at the minimal level using this method, and then you sort of propagate that eventually to non-minimal levels as well. And that requires more work beyond this.
My question was whether R equals T needs to be proved for application to semi-stable elliptic curves for non-minimal case also, or only the minimal case? Perhaps non-minimal case.
R equals T needs to be proved, yeah, in both cases, yeah.
For application to FLT?
Yes.
Those are non-minimal?
Yes, absolutely. So yeah, so for the application to FLT, so you have your Frey curve, right? And the property of the Frey curve is that its conductor is large, but the Artin conductor of the residual representation is very small. So it's, I mean, the conductor of the elliptic curve is highly non-minimal. So proving R equals T at minimal level is not enough. You have to prove R equals T at the non-minimal level as well. Eventually, argument. So one of the main components of this argument is the level lowering theorem of Ribet. So of course, so you have your Frey curve giving rise to your giving rise to this. So you start with your Frey curve, and then you look at the residual representation of the Frey curve. The residual representation has very small Artin conductor, and therefore by Ribet's level lowering, you sort of know that this is coming from. So therefore you can actually level lower, and eventually you sort of get a modular form. I think it's basically a modular form of weight 2 on gamma naught of 2, which does not exist. The point is that you can sort of, after using the level lowering step, you actually get a modular form on gamma naught of 2. And it's such a thing. I mean, basically, you don't have such a modular form. There doesn't exist such a modular form. So the level lowering step is also used there. But for establishing modularity of that elliptic curve to begin with, you do need R equals 2 at the non-minimal, in the non-minimal case as well.
Yeah. Good. All right.
Could you suggest some references for introductory and for recent development in 20 years?
Yeah. So I think, I did this lecture with the hope that, like eventually in this course, all of these notions will be developed in a more systematic way. And so, for instance, I would suggest looking at, the main reference is, of course, at a graduate level would be modular forms in Fermat's last theorem. So that's like a textbook which sort of grew out of the Boston seminar, which sort of took place, a while after Andrew Wiles proved the result.
Like that,
So that is
Silverman and other thing, Tate Silver, some conference
Yes.
you are saying, right?
Yes, it's exactly. So it's a Springer book, which basically is based on the Boston conference. So that is definitely one reference. I did look through some parts of Wiles's paper once, but again, like a lot of the paper is kind of difficult to follow. But then, yeah, but I think that book actually goes through this in a good amount of detail.
So while going for the modularity from Q to other totally real number field, we need the Hilbert modular form. So what are the status of these theorems, like Wiles lifting theorem for those stuff for abelian variety?
Yeah. I think so. First of all, I think there isn't much known for abelian varieties. I think there's some like recent work done for abelian surfaces, but the picture is like far from complete for abelian surfaces. I think there are some results of George Boxer and others on this topic. And then for totally real fields, I think that is a situation which a lot more is known. So I know that the level lowering theorem is more or less known, I think, in the totally real fields case. And there's also, I think, I think the modularity theorem is also known. I think the reference would be there's some papers of Fujiwara on the totally real field version of these type of.
No, Freitas has proved this over the quadratic number field, right? Modularity.
I'm not 100% sure, but I think I'm not at the top of my head. I don't remember like what the literature is on totally real fields, but I think as far as remember, like I went through some parts of Fujiwara's papers, and he seems, I think he was, in my opinion, I felt like he had proved a lot of the statement, but I might be wrong about this. But yeah, so I would start with Fujiwara and see what he says about the state of the art there, and just look at some papers that might be sort of citing his paper. Yeah, I'm sorry, I don't know anything beyond that, but
okay, thanks. We will check.
Yeah, I understand why you might be interested in the totally real fields case, because
basically Darman's program discusses the modularity of abelian variety over those fields.
Yeah, exactly. So that would be something to look into, of course.
Okay, thanks.
I mean, the level lowering theorem is definitely like very important in those results, I'm sure.
All right, very well. If there are no more other questions, then let's thank Anwesh again, and we end the meeting now. So thank you, Anwesh. Very good talk.
And
Okay.
Thank you both.
You are in UBC. What is the local time?
4 a.m.
Oh, it's around 3:45.
I mean, that's really inconvenient hour for you.
Well, I mean, it's not that inconvenient because the semester is not started yet.
Okay.
So I don't have to teach any class tomorrow, thankfully.
Okay, okay, all right. Okay, so I hope you can sleep. All right, thank you. So I think that's it for the moment. Bye.
Yes.
Thank you so much
for sharing the session.
Of course. Yeah, yes, my pleasure.
Yes, thank you.
All right. Goodbye. Thank
Bye.
you so much.
Yes. So put Devendra, please put off this thing. I mean, record.